name's Clayton Mangette, and today I'm going to be covering the work that we've submitted to IROS on multi-robot coordinated planning in confined environments under kinematic constraints. The motivation for our work is to address the multi-robot path planning problem in the use case of confined environments. So a motivating example for this is a traffic intersection with multiple autonomous vehicles, where each vehicle has its own goal to go from point A to point B, and they have to navigate through a shared space. Additional applications include the warehouse path planning problem, where you have a number of robots moving inventory through tight corridors, and UAV traffic control, where you have a number of UAVs occupying the same airspace. The problem framework that we work with is the multi-robot path planning problem, and that is that given some initial configuration and final configuration that we denote as QI and QF, which in this context is a joint configuration, we would like to find a path from the initial configuration for each robot to their final configuration, a joint path, that is. And the goal is to do so while avoiding collisions with the environment and avoiding inter-robot collisions. An additional goal of ours is to reduce runtime of the planner, specifically in confined spaces. And this is a challenge in the multi-robot path planning problem due to the exponential growth in the planning problem. So as you increase the number of robots in your planning space, what you'll see is that the time required to find a solution grows exponentially. And this is exacerbated in confined planning spaces because there's a high likelihood of collisions that will occur. The work that we base our own work off of is called discrete RRT, or DRRT, which itself is a multi-robot extension to RRT. And the basic premise behind DRRT is to break down motion planning into two steps. And the first step is a local planning step in which each robot forms its own map from its environment to go from its initial to its final configuration. So you can see below, this would be an example of a roadmap building stage where you input your initial and final configurations, you give the map some connection radius and resolution requirements, and you form a graph where vertices represent configurations and edges represent feasible paths between those configurations. And this is repeated for each robot. The next step is the central planning stage, in which the inputs are now the outputs of the previous step, which were the roadmaps. So each robot has its own roadmap, as you can see down here on the left. And the idea behind DRT in the central planning step is to start at your initial configuration, like in a normal RRT algorithm, and sample not directly from the configuration space, but sample from these roadmaps that you previously computed. And the advantage of doing this is that because you're sampling from those roadmaps instead of directly from the configuration space, those previous roadmaps have already been collision checked against the environment. So you save time in the planning stage, in the central planning stage, and you only have to collision check between other robots in your environment. And then, like in normal RRT, in DRT, you would extend your tree by by randomly sampling configuration, determining which configuration in your tree is the nearest configuration, and then incrementally moving towards Q new, or towards a new configuration. And then one note is that most of our work is based off of DRT star, which was a more recent development or more recent advancement of DRT, in which you save time even further in the planning stage by switching between random sampling and randomly sampling your environment and greedily expanding towards the goal region. Our work is to modify DRT star into a new algorithm, which we called fast DRT. And the premise of this planner is to reach a solution quicker and to prioritize finding a solution quickly. And we do so by adding in a greedy connection strategy that's invoked every time a collision is detected. Furthermore, we in our use cases and in our test cases, we extend DRT star to robots under kinematic constraints, and specifically Dubin's constraints. And what we find as a result is that there's going to be an implicit trade-off between solution quality and runtime of the planner when we compare it to DRT star. The premise of the greedy connection strategy, if we look at a motivating example, is to modify the behavior of the algorithm when a collision is detected. So if we look at an example below here, to the lower left corner, we have robots I and J that are moving from their respective Q1 and Q2 configurations. In the original algorithm, if a collision is detected, that new configuration Q2 is simply thrown out and expansion fails in that step. In fast DRT, in our proposed system, instead of throwing out Q2, we form a hybrid configuration between those two configurations. So in this case, some robots will move forward to Q2 while some will stay put at Q1. And the idea behind that is that while in most cases, when a collision is detected, there may be one or two robots conflicting with one another, but the rest of the robots may have no sort of conflict with one another. So is it really that efficient to completely throw out a new configuration, or is there some compromise that can be made where some robots incrementally move towards their respective positions while others hold their positions? And the greedy connection strategy functions by first determining the local priorities between each pair of robots. So it iterates between each pair of robots and determines how these robots interact, and if there's a collision that occurs, which robot should be given a local priority between the two. So from this determination, we form 3 sets for each robot. So the ith robot is given L of I, the set of all robots with respect to robot I that have a lower priority, meaning that robot I should move ahead of them. H of I, the set of robots with a higher priority than robot I that robot I should yield to. And U of I, robots that collide with robot I, but it's undetermined whether one robot should move over another. And the second step will simply be to greedily add robots to the solution set based off of these previous priority sets that we've determined. And the local priority rules that we've decided on is that we pick the robot that is the least obstructive, and we give that robot priority. So an example of this to the left here is we go back to the example of robot I and robot J. If we move robot J from Q1 to Q2, you can see it blocks the path of robot I that wanted to move from Q1 to Q2. So in this case, because robot J is obstructing robot I's path, we say robot I has priority over robot J. And as a result, robot I would be added to the lower priority set, or robot I would be added to the higher priority set of robot J, and robot J would be added to the lower priority set of robot I. A special case for this is, you see on the right here, where a collision is detected, but neither robot obstructs the other's path. So in this case, because it doesn't really matter who goes first, because neither one is obstructing the other's, neither one's final or initial configuration is obstructing the other one's path, either one can move forward, and they're both added to each other's respective undetermined priority sets. And the second step in this is to form the solution set S. So for each robot, we're going to look at the local priority sets for each robot. So if the higher priority set and the undetermined priority set are empty, that implies that robot I has no conflicts with any other robots. Or if it has any conflicts with any other robots, it maintains a higher priority over all its conflicting robots. So we add it to the solution set. In the second case, if robot I's higher priority set is not empty, we reject it from the solution set. So that if any robot has a hard priority over robot I, we reject it outright. And the third case is if its undetermined set is not empty, I should say, and its higher priority set is empty, then that means that there are some robots that conflict with robot I, but we don't know who should be given priority in this case. So in this event, we look at the cost of adding robot I to the solution set, which is simply just the size of its undetermined priority set. And the significance of this cost is that it's saying, how many robots are we excluding from the solution set if we add robot I to the solution set? And so we add robot I to the solution set if its cost of adding to the solution set is less than the cost of adding any other robot in its undetermined priority set to the solution set. So an example of this is listed below is that go back to the example of robot I and robot J, where robot I has an undetermined priority of robot J, and robot J has an undetermined priority of robot I and another robot K. We would say that robot I would be added to the solution set because it has a lower overall cost compared to robot J. What this looks like in practice is that you first plan the local road maps for each robot. So in this case, you can see a robot is turning left and it's planning its local road map here. And this is what its PRM would look like. The next step is once you have the local PRMs, you'll run the central planning step and it will find a solution. And this is a typical runtime for a worst case traffic scenario. And the third step is execution of the paths right here. So what you'll see here is that although routes come very close to each other, they do not collide with one another, and they're able to reach their respective initial and final configuration safely. We tested our algorithm in 3 different environments of increasing complexity, from a UAV environment, which has no obstacles, to a warehouse space with a number of obstacles that force the robots into confined spaces. And what we find is that as the confinedness of the space increases, when compared to DRT star, our algorithm is able to find a solution on average much more quickly. And if we compare the normalized average solution times and the normalized average solution cost, what we find is that there's an implicit trade-off between picking between the two algorithms. So in our case, as the confinedness of the space increases, which we don't have a good quantitative metric for, but qualitatively, as the confinedness increases, the solution time for DRT star grows much faster than our algorithm. Conversely, as the confinedness increases, the solution quality of DRT star is considerably higher. And in this case, when we refer to solution quality, we just mean the average path cost, which we've normalized. So in conclusion, the work that we've shown, I think is fairly promising, but it has some shortcomings that we'd like to address. One of which is theoretical guarantees of the algorithm, which we don't expect to be too different in terms of complexity from DRT star, but we would like to give exact theoretical guarantees on the completeness as well as the complexity of the algorithm. And then a future research problem that we're interested in is the online planning problem that we've done some preliminary work on. So can we adapt multi-robot planning to replanning? So can paths that have already been made for, say, 6 robots in an intersection environment be replanned in a timely manner? So I want to thank you for coming to this presentation, and I'll open up to questions.